All right, does anyone have restrictions for number 1? What can't x be? Can't be 2, because that would make the denominator 0. Number 2, anyone have restrictions for number 2? What can't x be? -5. And there's 2 things that x cannot be for number 3. Also, we can simplify number 3. If we factor both the numerator and the denominator, then a factor of x plus 1 cancels, so we can simplify it to x minus 3 over x minus 2. But what will the restrictions on the domain be? They can't be 2 and they can't be -1. So even though this factor cancels, it was part of the original function. So we have that x cannot equal 2 and x cannot equal -1. Raise your hand if you know what's going to happen where x equals -1 since this factor canceled. 1 person remembers. 2 people remember. You guys want to say what it is? You're going to get a hole. This will create a hole in the graph, which is an open circle, where x equals -1, and we'd have to plug it into the function to figure out what the height would be. I don't know what it would be. I'd have to plug it in here. So that'd be actually -1 minus 3 would be -4 over -3, so it'd be +4/3. So 1 1/3 is where the height of that hole would occur by plugging it back into the function, because a is our reduced function. All right, we're going to go back to number 1. You guys looked at your graphing calculator. You should have seen that a restriction on the domain was this value right here. In fact, oh no, we already talked about restriction on the domain. Using a graphic calculator, find the zeros. Does anyone have the 0 for number 1? No? Yes, sir. 1.8 is what you got. All right. So how do we do that on our graphing calculator? We can use the feature that we used before. We could also do this algebraically, which we'll be looking at today. But we've got the function 1 over the quantity x minus 2 plus 5. When I look at the graph, I can see it crosses right there. I can do calculate 0. I'm now to the left of that 0. Oh, went too far. Now I'm to the right of that 0, and it does give me 1.80. So x equals 1.8 is the 0, or the x-intercept. We do have a vertical asymptote. You could see that on the graph. That happens at x equals 2. We don't see the dashed line that we draw when we draw our graphs. Our graphing calculator doesn't do that, because then it can confuse us about the other lines. So x doesn't equal 2. That's a restriction on the domain. That's because there is a vertical asymptote at x equals 2. And there's also a horizontal asymptote. It's up here, 1, 2, 3, 4, roughly at 5, at y equals 5. Horizontal asymptote at y equals 5. A little hard to see on the graph, but some of you might remember the rules. When you first looked at functions that had a solid number in the numerator in Algebra 1 and a variable in the denominator, any sign on here will make it move the opposite of what you see. So the -2 makes our vertical asymptote, which for the original parent function of f of x equals 1 over x, it gave us this graph. We had a vertical asymptote at 0 and a horizontal asymptote at y equals 0. When we have the -2, what you learned in Algebra 2 is that translates the graph to the right 2 units, which is why our vertical asymptote is now at 2. And then the +5 shifts every point on the graph up 5 units, giving us our vertical asymptote at 5 instead. But we'll be looking at more so ones that have polynomial expressions in the numerator and denominator. So for this one, the 0, we could find algebraically, but I believe you should have had 1.5. Is that what you guys got for that one, or no? 1.5, yeah, like 3/2 for the 0. Again, you could get that on your calculator. I'm getting it from looking at the equation right now. But I could, in parentheses, put in my 2x minus 3 divided by x plus 5. When I look at the graph, I can find that using the calculate the 0 feature on the calculator. I'm to the right, left of it. Now I'm above it to the right, 1.50. I can find the asymptotes, appears to be right here. The vertical at -5, x equals -5, so the vertical asymptote's at x equals -5. The horizontal asymptote appears to be, I see part of it over here. It's a little harder to see the horizontal asymptote, maybe if I zoom out, but then I'm not going to see the axis. The horizontal asymptote's actually going to be, you might have had a hard time getting that, at y equals 2. We'll talk about that in a second. It's not at 0 because this crosses over the x-axis and keeps going. It's actually shifted up. It's right there at 2 if I shot that across this way and this way. And then for number 3, we have our factored form. We know we have a hole. So we have a hole, and I didn't have this, but written down for you, at -1 4/3. We also have a vertical asymptote at x equals -2. By the way, your calculator, most of them are not going to put the hole in the graph for you. So you have to know that it's there. Even if you put this function in, it's still going to graph it usually without the hole. And letter E, the horizontal asymptote should have been at y equals 1. It should have looked roughly like that to look like it was approaching that value. I think that's all I asked for was for those parts. Questions on finding those on the graph and calculator? Some of them are hard to find. It's hard to find the horizontal asymptote. Sometimes it's even hard to find the vertical asymptote in the graph and calculator or the hole. So we're going to look at that. On the back, we're going to talk about some big questions that you should know from Algebra 2, but it's been a while. And again, it was just a section and everything else you had to learn. How do we find this stuff without a graph and calculator? To find the zeros for any function, what do you do? If you have f of x equals something, you'd set the function equal to 0. Well, here's what's going to happen when you do that. So I've got, what I have is I have a polynomial on top and a polynomial on bottom, and I have now set it equal to 0. Well, to clear my denominator, I multiply by q of x. What's 0 times anything? 0. So now I have 0 equals p of x. So what we're basically going to do to find the zeros is we're going to set the numerator, the expression that's in the numerator, equal to 0. Set numerator equal to 0. And then you'll find your zeros. You'll only have one if it's a linear expression. If it's a quadratic expression, you could have 2 or 3 or more. So we have that. And if I look back, you don't have to flip back, but if I look back at this one, here's my numerator, 2x minus 3. When I set that equal to 0, I'm going to add 3 and divide by 2. 3 halves is 1.5, which is what we had for our 0. How do I find the vertical asymptotes? Well, when the function is simplified, you set the denominator equal to 0. So q of x gets set equal to 0. When the function is simplified, set the denominator equal to 0. So on our other problem, which was 2x minus 3 over x plus 5, it's already simplified. If I set that denominator equal to 0, I get x equals -5, which you guys knew was a restriction on the domain. But in this case, because it's a vertical asymptote, or because it's a restriction, we're going to have a vertical asymptote there. How do we find the x and y coordinate of a hole? Any factors that divide away or cancel out in simplifying. So any factors that cancel out and simplify, we're going to set equal to 0 to get the x coordinate. And then we're going to plug that x coordinate in. Into the function, or into the remaining function, to get the y coordinate. So we're going to take the x coordinate that we get from when the factor that canceled, and we're plugging it into the equation, whatever equation is left after we've reduced, or even before, it should still work. It's easier to plug it into the reduced one. The remaining function will get our y coordinate. And that's what we did on that one example, where we had the factor of x plus 1 canceled on that last problem. So I said, well, where x equals -1, you get, two of you said that there would be a hole there. And so then I put that into my calculator. The remaining function was x minus 3 over x minus 2. So all I did was -1 minus 3 over -1 minus 2. And that's how I got my answer of 4/3. To find the horizontal asymptote, there are actually 3 cases that we have to be aware of. Okay? So we're going to talk about the degree of P of x and of Q of x when we have our function, our rational function equaling P of x over Q of x. If the degree of P is greater than the degree of Q, I feel like I'm going to mess this up. I know it. Hold on. Let me look at something real quick just to double check this. X squared. That's going to be a line. Then there will be, then there will be no horizontal asymptote. So that's case 1. There's going to be 3 cases for this. And so you have to look at their degree to decide what to do. If the degree of Q of x, the bottom, if the degree of the denominator is bigger than the degree on the top, then the horizontal asymptote will be y equals 0. Yep. And if the degree of P of x equals the degree of Q of x, then the horizontal asymptote is y equals the lead coefficient, that's what I use for L, that's what LC means, lead coefficient of P over the lead coefficient of Q. So we'll look back at our other problems in a second to see how these work. I'm going to get another worksheet. So LC is lead coefficient. So I'm just looking back at this other page. I'll leave the rules up there so we can see it as we look at it. All right. So that's our rules. If you look back at our graphs, this first one, the degree of the bottom is bigger. See, degree of Q is bigger. Our horizontal asymptote for that one was y equals 0. For number 2, the degrees were the same. X to the first, x to the first for the numerator and the denominator. When they're the same, I have to do the lead coefficient of the top over the lead coefficient of the bottom. So it was y equals 2 over 1, which gave us our y equals 2 horizontal asymptote. And then on number 3, they were also the same. This was y equals 1 over 1. So y equals 1 was the horizontal asymptote. All right, so how do we describe the end behavior? That's what we want to look at. I'm going to look at a function of x over x squared just to see what happens. X over x squared is going to have a horizontal asymptote, since the denominator is bigger, of y equals 0. And I can even see that on this graph. So what's happening as I go to the right? What's happening with this graph? It's getting closer and closer to what? To the x-axis. It's getting closer and closer to a height of 0. And as it's coming up on this side and going to the left, it's getting closer and closer to a height of 0. So unlike our polynomial functions, which shoot up toward infinity, for a rational function that has, this is if it has, a horizontal asymptote, then the limit on f of x. Now, there are some that don't have a horizontal asymptote, so it is possible for them to still act like a polynomial. Let me show you an example. If I had x squared over x, that's actually going to just give me a linear function anyhow, but you'll get the idea. So there's no horizontal asymptote for this that started out as a rational function. This one would still be, as I go to the right, it shoots up infinitely. As I go to the left, it shoots down infinitely. But when they have a horizontal asymptote, the limit as x approaches negative infinity and the limit on the function as x approaches positive infinity, what's going to happen to the height is it's going to get closer and closer to whatever the horizontal asymptote is. Sometimes it can actually touch it or cross it, but it's rare. There are cases where it can. A lot of times it just approaches it. But either way, it's going to continue approaching that horizontal asymptote. So when I had x squared over x, or no, sorry, x over x squared, I could click trace if I want. It's just getting closer and closer and closer to 0. You can see those y values going down. And they just keep going down. And it's eventually going to say e to the negative whatever, okay? Because it's just going to get closer and closer. It keeps jumping on the graph, but you get the idea. So it's not shooting up infinitely or down infinitely. It's approaching the horizontal asymptote. And that's something that we haven't seen before that's unique for rational functions. Not just rational functions. It'll come into some other functions, but from what we've looked at so far, it's unique. What do you need to be careful of when writing the domain and range? Well, the domain will be affected by the vertical asymptotes. You have to take out any vertical asymptotes and any holes. So normally you'd be like, hey, my domain's negative infinity to positive infinity. Well, that's true. This function is not continuous, though, because it has vertical asymptotes and holes. So whatever those x values are, my domain can't include those. So when I'm doing interval notation, I'll need to break up the intervals at those places. For the range, what do you think is going to affect the range? The horizontal asymptote. So the range, we'd have to take out the horizontal asymptote. And then other than that, it should go up infinitely and down infinitely, and we'll be okay with that. Not the end behavior of it. The end behavior of it approaches the horizontal asymptote. But when we have that vertical asymptote, this one shoots up infinitely and this one shoots down infinitely. So all values of y are covered except for the horizontal asymptote. So as we go to our notes today, you want to memorize these facts about rational expressions, but you can consider this for now, your little cheat sheet, not that you'll have it on an assessment, to help us as we're looking at these problems and trying to review and remember these rules. So we're actually going to skip all this. I should have taken it off of here because we just did all that here. It gave you more space to lay it out. You saw it from the warm-up problems. For each of these functions, we are asked to For these rational functions, we're asked to graph the rational functions and their asymptotes and holes and all that wonderful stuff. You can't see that. Let me zoom in more. For each function, determine any asymptotes, holes, and intercepts. That would include the y-intercept because they didn't just say zeros. Then graph the function and state its domain. So where to start? All right. We're going to start by seeing if this function will simplify, and I think it does, because this is x minus, no, it's not going to. 5 and 2 won't. It's not going to reduce. X minus 5, x minus 2 won't cancel out, so we're okay. It will still help me get the zeros. So x minus 5, x minus 2, that multiplies to negative 10 and adds to negative 7. Since that's my numerator, that's going to help me get the zeros. The zeros will be x equals 5 and x equals 2. And I can plot those right now on my graph. So it does say the intercepts, so I do need to get the y-intercept. To get the y-intercept, I'm just going to do f of 0. So I plug 0 in, and everything in my numerator disappears except for 10. Everything in my denominator disappears except for x. So it's 10 over negative 3, which I'm going to want a decimal value for graphing that. Negative 3 and 1/3, or negative 3.3 repeated. So there are my intercepts. I've just answered that right here. There's the intercepts. And I'll plot that one also. Negative 3 and 1/3 is roughly there. For each function, find any asymptotes. So that includes both horizontal and vertical. Am I going to have any holes for this function? No, because nothing canceled, so not applicable for this particular function. So I should have written that here. Holes, not applicable. No factors canceled. But for our vertical asymptotes, where do I get that one from? Where's the vertical asymptote come from? I need to look back at your other sheet, but it comes from the restrictions on the domain, which are that x can't be 3. So in this case, I'll have one at x equals 3. So I come over to my graph, and where x equals 3, I'm going to do a dashed line to show that that's a vertical asymptote on my graph. And horizontal asymptotes, that's, in this case, this one the numerator has a degree higher than the denominator. So that means that there is, I think, no horizontal asymptote, right? Yes, no horizontal asymptote. Degree P is greater than degree Q. So there's no horizontal asymptote. And if I put this in my calculator, I should see that. And I can also see which way it behaves. Although I'm pretty sure right now, from looking at this, that this is what I have, that this is coming down on a curve and shooting up along this asymptote. And then, well, I'm pretty sure, let's double check that. So in parentheses, I have my numerator x squared minus 7x plus 10. And my denominator, I have x minus 3. Yep, that's exactly what it does. And then from here, it comes from the bottom of the asymptote. They should always split. If one's going up this way, the other one's going down here. This comes up from the asymptote and goes through this line and then continues shooting up. Just like it does in the calculator. I don't quite have the angle it does it at, but I have the general trend, and that's fine to have the general trend of the curve. I'm also supposed to state the domain, and I'm going to throw the range in there too and the end behavior because I know we're going to be assessed on that later. So our domain for this is affected by the vertical asymptotes and holes. So I'm going to do that in the same color. Domain right now, this is going to keep going left, and this is going to keep going right. So it would be negative infinity to positive infinity, except for what value? What value can't x be? 3. So from negative infinity up to 3, joined with from 3 to positive infinity, and because it doesn't have brackets, I'm showing that it does not include 3. If there were 2 horizontal asymptotes, I would actually have 3 intervals here, because I'd have another one between the 2 horizontal asymptotes. And then I am going to throw on range and then behavior, at least for this one. Our range, you can see it's going to go down infinitely and up infinitely, and we have no horizontal asymptotes. So it's negative infinity to positive infinity. And the same thing with our limits, right? If I'm looking at n behavior, it shoots down infinitely and up infinitely. So the limit on f of x, as I go to the right, it's shooting up. The limit on f of x, as I shoot to the left, it's going down infinitely. So I didn't ask for those 2 parts. I just added those 2 parts so that we can discuss them because they're going to be coming up. All right, any questions on that graph or how to get those points? All right, so I'm going to be calling on people to help me solve the next one, and then I'll give you a chance for one function on your own. So, wrong class. Mr. Bonkowski, what can you tell me that I could find from this? Anything. Give me anything. You can pick from that list of things. Give me something I can find about this function.
The bottom's not factored.
It's not. Well, it's not. It is. Yep, it would be x minus 2 by x, or no, x plus 2 by x minus 1. Multiply negative 2 adds to 1. So it is factorable. But will anything cancel? No. So in this case, I don't have any holes. She's not here. Kiana, what else can you tell me about it, since we're looking at that denominator right now? So that'll be our restrictions on the domain, which means they're also the what? What always comes from the denominator. Who can tell me what comes from our denominator? Michaela? Vertical asymptotes, yes. So are the ones that Kiana said we can't have for x, those are our vertical asymptotes. X is going to be negative 2 for the vertical asymptote. X is going to be positive 1 for the vertical asymptote. So on my graph, I'm going to go over to negative 2 and do a vertical dashed line. And at 1, I'm going to do the same thing, a vertical dotted or dashed line. So that's our vertical asymptotes. We have to look to see if there are horizontal asymptotes. In this case, the denominator has a degree higher than the degree, which is 1 of the numerator. And so that means that the horizontal asymptote is going to be 0. So at y equals 0, I'm going to do a dashed line. Now there's some things I didn't find yet. What else do I need to find? Who can tell me? Let's see. Hunter, what is something else I could find for this? We haven't found our intercepts yet, right? So how do I get either my x or my y-intercept? How do I get it? Yeah, for y-intercept, I do f of 0. For x-intercept, I set the numerator equal to 0. So in this case, x does equal 0, which is going to be the same as my y-intercept. So when I plug 0 and I get 0 over some number, so it's going to be 0. That's the y-intercept. And they're the same in this case because the x and y-intercept are 0, 0. So I'm going to plot that right there. 0, 0 is my 1 intercept. All right, so that's all of it. Now we need to look at the graph to see what's going on. I have a suspicion that we're either going to have a curve here or here, and then the maybe the same down here or up here. And in here, it's going to like kind of do a crazy, almost like a cubic function, but bounded by those vertical asymptotes. So we're going to put our function x over, in parentheses, x squared plus x minus 2. And we hit graph, and I'm going to zoom out, or zoom standard. And sure enough, actually it's down here and up here, and it's approaching 0 and approaching this vertical asymptote, approaching 0, approaching this vertical asymptote. So on my graph, that's what I'm going to show, that here it's approaching the vertical asymptote, and then down here it's approaching the horizontal asymptote. On this side, going left, it's approaching the horizontal asymptote. Going right, it's approaching our vertical asymptote. And then between it does this, like, it almost looks like the cubic function, how it twists. But there's that vertical asymptote that it's approaching on the left as it goes up, and on the right as it goes down. So on the left as it goes up, and on the right as it goes down. And so there's my sketch of my graph with all the most critical things stated there. Our domain for this, we don't have any holes. That's good, but we do have vertical asymptotes. That would have been the restrictions that Kiana told us about earlier. So the domain otherwise goes left forever and right forever, but it cannot be -2 and it cannot be 1. So it goes from -infinity up to -2. And then you're allowed to have a graph or points on the graph between -2 and 1. And you can have points on the graph from 1 to infinity. I'm going to add the piece of the range. The range, this goes down forever, and this goes up forever, but, oh, and here's the trick. Usually the horizontal asymptote, we would say it couldn't be part of the range, right? But what's going to change that? Do you guys see? Our horizontal asymptote is y equals 0, right? So we usually say that affects our range, which usually it does. But see this point right here? Where's that point at? 0, 0. So it's at a height of 0. So it actually is covered. Even though there's a horizontal asymptote, there's a point on there in that middle section. And so we actually have -infinity to positive infinity. This is one of those unique cases where it doesn't affect it. We'll talk about limit behavior later. I'm not going to do that right now. Try this last one. Make sure you factor. If you're not sure about your factors, check with people at your table, see if they got the same factors before you start answering things. When I want to find the zeros, what part of this do I look at? Numerator or denominator? To find the zeros. Numerator. If I want to find the vertical asymptotes, I look at the denominator. And any factors that cancel will give you wholes. So take a second to look at those. All right, who could tell me the zeros or the intercepts? What are the zeros and the y-intercept? So we do have a factor that cancels here, right? So I heard somebody say, was it you, Kiana? Okay, what's our x-intercept? 0. Or not 2, 2, right? You said 2 initially. X equals 2. I get that by setting that factor equal to 0. So at 2, I'm going to put a point. And then for our y-intercept, I'm going to plug in 0. So I've got -4 over -8, which is positive 1/2. So I'll put a point there for my y-intercept. All right, who can tell me what the vertical asymptotes were? Nobody can? Yes? Thank you, Jennifer. Vertical asymptotes. Oh, we got to be careful. One of them is 4. The -2 would have been, except it cancels, right? So instead of a vertical asymptote, what am I going to have there? A hole. And so that'll be at x equals -2. It'll be -2. We have to figure out its height. So I'm going to plot the vertical asymptote of 4 right now. And then for my hole, I'm going to plug -2 back into this reduced function. You could put it into the original, but it's more work. So I got -2 minus 2, which is -4, and -2 minus -4, which is -6. That reduces to +2/3. So at -2, -2/3, it's just less than 1. I'm going to put an open circle. That's an open circle there. And I did put it in the right place. The graph is kind of small, sorry about that. The ones that you work on for homework will be bigger. All right, who has our horizontal asymptote? Anyone know what the horizontal asymptote is for this? 1, yes. We have the same degree on top, same degree on bottom. The lead coefficients are 1. So y equals 1 over 1, which is 1. So at y equals 1, I put a horizontal line, dashed line for my horizontal asymptote. I think that was everything we were supposed to find to do our graph. I'm pretty sure I know what happens on this side of it. Maybe not. I might need to look at my graphing calculator to see what's going on. So I'm going to put the function in. I have x minus 2 in parentheses over x minus 4 in parentheses. Oh, I think I put my open circle at the wrong spot. You guys didn't say anything. It's at -2, +2/3, right? That's why I got confused on my graph. This is in the wrong spot. It should be up here. Up here should be my open circle. And that makes more sense with my graph because then my graph is going to come up, have that open circle there, and then keep approaching that horizontal asymptote. Then it's going to come down and approach this vertical asymptote. And then up here, it approaches the vertical asymptote as it goes that way, and as it goes this way, it approaches the horizontal asymptote. And that completes our graph. For the domain, which is what I had asked for originally in the function, it's going to be everything except for what those restrictions were, that hole, the x value of the hole, the x value of the vertical asymptote. So it's going to be -infinity up to -2. And then it does continue from -2 up to +4, but not including +4. And then from +4 to infinity. And I can see that on my graph as well. It goes left forever, doesn't have an x value there at -2. Between these, there's points, and past that vertical asymptote, there's points. So there's my domain. So hopefully using this chart until it's memorized, although most of you it's coming back to you now, you can use those things to help you find these and graph rational functions or do a nice sketch of them. These are the practice problems. It is odds. The review problems are recommended. They'll help you as we're getting ready and moving toward our next quiz and our BA. But these ones are required to qualify for reassessment. So you'll want to work on those.